Hello everyone. So today, could you guess what is my appearance for today? Okay, this is our last chapter. So today I decided to show you my true faces. And I am Totoro. We are going to end the chapter soon. So let's take out your worksheet. And today, what we're going to do is that we are going to um, formally introduce Lenz's law to you, and we will try a few questions, and then we'll watch some video. So I think in total you will spend 30 minutes on this, and after that we can call it a day. Okay, so let's take out a worksheet and we will begin.
Okay, so we will begin with a quick recap on what Lenz's law is. So on the other day, I was telling you that Lenz's law is like what we encounter in a very typical PGR romantic drama, whereby when the boy is trying too hard, getting too friendly, then the partner, the girl, will tend to resist and push him away. But when the guy decided to have enough and decided to leave, then sometimes the female lead may decided to, oh no, he's leaving, and want to attract him back. So Lenz's law can be interpreted similar to that. So for example, if we look at this example where I label 1 now, you can see that the magnet is swinging from this position to the center, so from right to the left. And if I have a solenoid on the right side, what will happen is that because the solenoid will experience a decreasing magnetic flux linking to the oscillating magnet. So you notice that the way I form my sentence, I would follow the sentence structure given earlier. So if you have forgotten, let's recap on that. For example, if I want to talk about why is there a induced current or a induced EMF, I would need to use this particular phase. So if you look here, just now when I'm saying this, when I say that the magnet has swing away from this particular solenoid, so I would say that the solenoid, this one, experiences down here, the solenoid, oops, what did I do? Okay, I will say that the solenoid experience a decreasing magnetic flux linking to the oscillating magnet. So down here, you can see that this yellow solenoid is experiencing a decreasing magnetic flux linking to this oscillating magnet. And as a result, there will be a induced current like that, and by Lenz's law, I would have a induced south pole over here, so that this induced south pole would resist this change. What is the change? The north pole of the permanent magnet, this one, is leaving. Okay, so basically what happened is that the induced current will definitely flow in a way such that the magnetic effect of the induced current will resist the magnetic effect that produces the current. So let me slow down and write down what I write. So first, there will be a magnetic effect that produces the induced current. What do I mean by the magnetic effect that produces the induced current? Is this north pole going away, so that the solenoid will experience this decreasing magnetic flux linking to this swinging magnet, right? Then Lenz's law says that the magnetic effect of the induced current. So when I say the magnetic effect again, I am referring to the magnetic effect that comes out from this yellow solenoid, the red current there. So this magnetic effect is referring to this guy over here. Okay, so this magnetic effect of the induced current would resist the magnetic effect that produces the induced current in the first place. So if you open up your textbook and you look at the definition of Lenz's law, you will see that the way they phrase it is Lenz's law states that the magnetic effect of the induced current would resist the magnetic effect that produces the induced current. So magnetic effect number 2 and magnetic effect number 1, they are different. So this is just to highlight to you. So what I'm showing you here is an example whereby the magnetic effect of the induced current, the magnetic effect of the induced current is trying to attract back this north pole that is going away. If now I point you to example number 2, then this is another case, because down here I would have a north pole approaching the solenoid. So that's why the magnetic effect, which is this red one, of the induced current is going to repel or resist this approaching north pole. So that is what Lenz's law is about. So let's formulate it in, let's jot it down formally in your worksheet. So let's go to your 22.1, your page 4. So down here you will see the definition of the Lenz's law. I will try to fill in the blank, but my memory is not very good, so always refer to your textbook, okay? So it states that the magnitude of the induced current is such that, the direction, not magnitude. So this one is the direction of the induced current. So in Faraday's law, please remember, in Faraday's law is about the induced EMF. So if you look here, Faraday's law is about the induced EMF, but for Lenz's law is about the induced current. Okay, so let me write it down properly for you. It's such that the magnetic effect of the induced current will resist. Okay, so it will resist the motion of the change that produces it. So instead of writing the magnetic effect that produces this, they just say the change. It's fine. Okay, just follow this one. Okay, so for example, when a north pole approach a coil, the induced current in the coil will induce so I have a north pole approaching a coil. So therefore, how would I resist this north pole approaching me? I would have to induce a north pole at the near end. So for example, if I have a north approaching a coil, then this coil will have a current such that there will be a north pole here, so that these two will resist each other. Okay, so now what happened is that this is your question 5. So I will give a short pause here in the video, and I want you to label. For example, I will show you one example first. So down here you can see that the north is leaving the solenoid. So when the north is leaving, how do I know it's leaving? You look at the arrow, it's being pulled away. So now the north is being pulled away. That means my solenoid will have to induce a south and a north over here, so that the south here would try to resist this north from leaving. And in order for me to have a south there, I need to position my right hand such that it looks like this, right? Right, so you imagine the coil is like that. So that I would have my north on this side. So if I look at this, then I look at my fingers over here, I would know that the current has to go up like that. And if I go by this drawing, that means it will be like that. So by looking at the direction here, I will determine by Lenz's law what is my pole here, and finally what is the direction of the current using my right hand grip rule. So to do this, to determine the direction of induced current in a solenoid, first you look at what is the direction of the change. Then by Lenz's law, identify the induced magnetic pole, and then by right hand grip rule, the direction of the current. So once you have that, don't forget, write down how your galvanometer will show. So like I said before, some of you are asking me, teacher, I understand the whole thing, but shouldn't your galvanometer looks like that since current flow towards the left? Yes, current flow towards the left, but if your galvanometer, right, point directly horizontal like that, it means the current is super strong, and that is rarely the case. So most of the time we will just put diagonal towards the side that the current is flowing. So I would pause over here. You have to pause your video, and then after that you try your B, C, D, E and F. Okay, so pause. So have you tried the question? Okay, I'm going to show you the answer. So for B, C and D, I would not go through the questions. You just check whether it's correct or not. If it is wrong and you can't figure it out, please book a consultation with me. Okay, for part E, it is a little bit tricky because now you see that it is not just moving in one dimension, but it is now being pulled down like that. So when the magnet is being pulled down like that, does the solenoid experience an increasing self or a decreasing self? So down here, we are not really talking about the dimension of the motion or the direction, but rather whether it's increasing or decreasing. So if now I pull away the south pole downwards, to the solenoid, it is still a decrease of south pole. It is experiencing a decrease of south pole. So as a result, to resist this change, if there's a decrease in south pole, it means that I need to induce a north here so that the south will not get away from me so easily. So because of that, I would have an induced north and an induced south over here. So down here, if you use your right hand grip rule correctly, you should be able to see that the galvanometer will point towards the right. Okay, now for question part F, actually it is more challenging question. So down here there is this keyword, it passes right at the center. And for those of you who actually bother to take out the textbook to actually read the textbook before watching this video, you will actually see that there is no current flow, and it is something that is very interesting. So what happened is that if you when the magnet is now right at the center, then something interesting will happen. So for example, this is the center line. If I look at the later half of the solenoid, okay, and I have it here like that. So to this later half of the solenoid, actually what happened is that they are experiencing an increase in north pole, right? So when the left half of the solenoid experience this increase in north pole, then obviously it will try to resist it by having it like that. Then how about the right half of the solenoid? So the right half of the solenoid, which is this green part, to the right half of this solenoid, the magnet is actually leaving. It means that the south pole is actually leaving. So to this green color part, then because the south pole is leaving, then obviously I want to resist, right? So to the green part, I would need to have an induced north here to actually slow down the leaving of the south pole, right? So what happens is that you will see this interesting thing. So let me use colors so that you won't be so confused. So the green part here are the induced poles for the right half of the solenoid. And then this blue part is actually the poles for the left half of the thing. So if you look at this, then what will happen is that if you look at the left half of the solenoid, in order to have north on the right and south to the left, then the current will have to go this way, right? Then if you look at the right half of the solenoid, in order to have north on the left and south to the right, then you will have the current like that. So it actually neutralize each other, the induced current. So we will talk about that more in this graph. So this graph, I will only talk about it when school reopens because it's a bit complicated. But what is interesting is this point here. You can see that again, when the magnet is right at the center of the solenoid, actually the induced current is 0. So the general concept is like how I illustrated over here. You have to look at when the magnet is inside the solenoid, you have to cut the solenoid into left half and right half to analyze. And if left half and right half are equal in the number of turns, then the strength of the induced current will be exactly the same. But because the direction of the induced current is opposite, they will neutralize one another. So for some of you who are having difficulty, maybe I will just cut it like that. So what happened is that some of you may be wondering, what do you mean by left half, right half? So left half down here, what happened is that the magnet is actually entering into the is actually going this way. That's why you would have the north over here to resist the incoming north pole. But to the right half, the magnet is actually leaving, and it's the south pole that is leaving. So that's why down here you have an induced north pole. So anyway, if you don't get it, just put a star over there, and then we will review it when we meet each other when school reopens. Yeah, so now now that I have formally introduced you to Lenz's law, right? Let's use our brain and do some brain exercise rather than to do TYS, because now this is non-examinable, so there's no point for me to keep drilling you on O-level question. We can do something more interesting. So let me ask you this question. Okay, let's say I have a magnet. I have two magnets, and then I drop it in through a pipe. So the first pipe that I'm throwing it in, right, is plastic pipe. The second pipe that I'm throwing in, right, same diameter, same length, is actually a copper pipe. So these are magnet. So when I let this drop from rest, that means as a free fall, which of these magnet will reach the bottom first, or do you think that they will reach at the same time? And just a kind reminder, magnet, right, does it attract copper? Is copper a magnetic material? So in your syllabus, magnetic material only have 4, right? I cannot sing. Iron, cobalt, is it nickel? I'm not sure. Then steel. So I cannot sing. The C is not copper, it's cobalt. COB something, I forgot already. But definitely not copper. So if copper is not a magnetic material and I drop a magnet in, will they reach at the same time, or one will reach first? So I'll give you a pause for you to make a decision. But I have to remind you, give you a hint. The main difference between pipe 1 and pipe 2 in terms of material is that plastic is a electrical insulator, copper is a conductor, and we are learning Faraday's law and Lenz's law. So I hope you have make a guess. I will show you the answer now. So this is what happened when you put a magnet through a copper pipe. So observe the way it goes. Is it a free fall? So on the outside, wait, let's watch it again. On the outside, it just dropped. There's no attraction. But on the inside, so why? So if you remember that we have Lenz's law. So what happened is that when you have a copper pipe and you throw a magnet in, so when a magnet is going through, what you can imagine is that this copper pipe, you have to analyze it section by section. So you analyze it as a ring. So if you have a ring and you throw a north pole in, then this ring is like a very thick solenoid turn, right? And when that happens, then Lenz's law says that this ring would experience, the ring is a conductor, right? So Faraday's law can apply to any conductor. So as long as the conductor can complete a circuit, a loop. So in this case, this circular conductor will experience an incoming magnetic flux linking to this north pole. So what will happen is that there will be an induced current flowing around this copper ring, and the direction of the current flowing around this copper ring will be such that it produces a north on top. So if you use your right hand grip rule, in order for there to be an induced north pole to resist the downward north pole, then your induced current need to flow this way. This way. Yeah. So when that happens, there will be a resisting force acting on this approaching north pole. So that is why if you have a copper pipe, you can think of it as a series of copper ring put together. So when this blue color magnet is falling down, there will be an induced current flowing around the copper pipe like this, and the direction of this induced current will actually induce an opposing magnetic pole to actually resist the falling magnet. So actually to the magnet there will be an upward resisting force. That's why it slows down. And this particular phenomenon is very, very useful for us, because for us scientists are very, very interested in creating motion, and if we want to create motion, we need to control it, meaning that we need to stop motion as well. And how do we stop motion? So before all these thing is discovered, to stop motion we need to really apply a contact force. For example, your bicycle, how do we stop the wheels from turning? We basically put two brake pads and then we clamp onto the wheel. So let's say this wheel is this is the wheel, then you will have a clamping pad like that. So it's a direct force, like squeeze to the thing, and there will be a lot of friction, there will be wear and tear. So what happened is that, how do we do this? If I want to stop, for example, an incoming object, I need to use a hand to slam it down and all that, right? I need to apply a contact force. So what will happen? If now I am swinging a magnet, how do I stop this swinging magnet? Or should I say, let's say I want to swing, let's say I have this, and then I have a copper ring, a very heavy copper ring, and then this copper ring is swinging towards you. So let's say I put your face over here, and then you are like, oh no, right? So how do I stop this? To stop this, very easy. You can just put a piece of very huge magnet. So when the copper ring is swinging towards the magnet, this copper ring will experience an increase of magnetic flux linking to the permanent magnet. As a result, by Faraday's law, there will be an induced current flowing around the copper ring, and by Lenz's law, the direction of this induced current will be such that it actually induces an opposing pole, right? So because of that, then there will be a resisting force acting on the copper ring, and it will slow down and it will come to a stop. So let's take a look at some of the application that is based on this concept. So before we watch this video, I just want to highlight to you, this video is actually made in the States. So the way they explain it, they are actually explaining it in terms of inertia of electrons to resist the realignment from external magnetic field. So that is one way of explaining as well, but since we do not talk about inertia of electrons in our syllabus, for us we will just use Faraday's law to explain why there is an induced current when there's a change in the magnetic flux linking to a magnet, and then we are going to use Lenz's law to talk about why is the direction of the induced current giving rise to a pole, to a induced magnetic effect such that it resists the changing magnetic field. So we are going to use that approach to explain, but later when you watch this video, you will actually hear the man saying that they want to talk about electrons resistance to realignment. So for us, we keep to our own way of explaining. So that one is applicable to your JC as well.
In this video, I will be exploring magnetic braking and levitation utilizing the inductance of large copper plates. These plates I picked up on eBay for a pretty reasonable price, along with some very strong neodymium magnets. Together they behave in strange ways. Copper is not magnetic, so they don't exactly attract each other, but at the same time this magnet doesn't seem to want to slip off very quickly. It drags across the plate slowly, like it's moving through a thick fluid. It's even more interesting if I drop the magnet on the plate. It slows down mid-air and gently floats to the surface. So if the copper is not magnetic, something else must be causing this. And many of you probably already know the answer has to do with electricity. When a magnetic field moves through copper and many other metals, it causes electrons to reorganize themselves and flow in a circular pattern perpendicular to the oncoming magnetic field. Of course, the electrons were perfectly happy being where they were before the magnet tried moving them around, and so they resist this movement by generating a temporary magnetic field of their own. There's no attraction or repulsion, just resistance to change. One way that we can prove this resistance is due to the flow of electricity is by replacing the copper plates with a copper coil. This coil of wire is not connected at the ends, and so it does not form a complete electrical circuit. If we tried to make electrons flow around this coil, they would have nowhere to go, and we can tell this is the case because when I drop a magnet through the center, there is no resistance. It falls through the coil as if it were not even there, no slowing down at all. If the resistance to movement we saw with the copper plate was an inherent property of copper, nothing to do with electricity, the magnet should still slow down, even with a disconnected circuit. When I do connect the two ends of the copper wire, now the magnet pauses as soon as it reaches the coil, and it takes a moment to make it all the way through. Electrons can now make a complete orbit around the coil in response to the oncoming magnetic field. And so the magnet slows down as its momentum is converted into electrical current. If I once again disconnect the coil and bridge the circuit with an LED, we can see a better indication of the electricity. The LED is very efficient, so powering it doesn't slow down the magnet quite as much as when the circuit was closed directly. This is a simplified model of how the majority of the world's electricity is generated. There are many different types of power plants, but most of them are just trying to figure out different ways to more efficiently move magnets through coils of wire. Now back to the copper plates. We can't so easily get electricity from these like we can from a coil, but the electrons are still flowing and cause very heavy resistance to a strong magnet. Because of this, we can do some interesting things like manually levitate a magnet above the surface. I'm doing this by holding a second magnet underneath the plate. It's not easy to make a magnet float in this way, but it is fun to practice. I found that using a very wide magnet on top and a smaller magnet underneath is the most controllable setup. I made a small stand to hold my copper plates out of wood and acrylic glass. The resistance to movement caused by the electrical inductance in the copper is the only reason this levitation is possible. On a surface without this property, a magnet will fly right off the side as soon as you try to lift it with a second magnet. Despite the resistance that we've seen to change, magnetic fields pass right through copper as if it were not even there, as we can see by how I'm able to rotate this small cube magnet from a long distance away, even with the copper plate separating the magnet in my hand. Replacing the disc magnet with this smaller cube in the earlier setup allows me to walk it across the surface like a little robot, and the motion damping provided by the copper gives me very precise control. Besides the generation of electricity, there are a few other practical applications for this sort of motion damping. High-speed trains and even some roller coasters use a magnetic braking system set up in a way very similar to this, with powerful magnets, usually electromagnets, elevated above a conductive surface. The magnets slow the vehicle down quickly without any surface-to-surface friction that causes damage in conventional braking systems between brake pads and rotors. My favorite tabletop demonstration of magnetic braking is to swing a magnet toward a chunk of copper like a wrecking ball. The magnet loses all of its momentum at the very last moment in a way that almost looks supernatural. It reminds me of a scene in the second Matrix movie where Neo stops bullets in midair. What's really happening is of course the same thing that has happened in my other examples. The magnet's momentum is slowed by opposing magnetic fields generated by the flow of electrons in the copper. And since the electrical energy isn't being collected by a circuit for any useful purpose, it dissipates into the lump of copper as heat. So the copper actually gets warmer every time I swing the magnet toward it, but by such a small amount that measuring the change would be very difficult. All of the things that you've seen demonstrated in this video are described by two scientific principles: Faraday's law of induction and Lenz's law.
I will end